2.2, it is homogeneous linear ordinary differential equations with constant coefficient. Okay? So this heading of the section contains everything that you need to understand for what type of differential equation we are solving. Okay? So homogeneous, which is R is 0, right? So that's the first logic that has, right? And of course this is second order, so we can only solve linear systems, right? Not only, but it's more easier to deal with linear systems, right? And constant coefficient, that's P and Q, are just real numbers. Okay? So this heading, homogeneous linear ODEs with constant coefficient, contains everything you need to have, right? So your equation for this type is this: a y prime plus by is 0. Okay? So here a is actually p and b is q. To emphasize that it's a number, we use ab instead of pq, okay? For clear distinction. So now you have a new type of equation, right? New type of differential equation. What are you going to do? If you see a new type, what are you going to do? Well, that's right. Try. That's good, right? Immediately, whenever I tell you, new equation, try. Okay? You just guess and try whatever the function you have in your mind, and you just try. Okay? That's the most basics of solving the differential equation. Right? That's good. All right. So naturally, you saw that exponential function was really good solution for the first order, right? And it's natural to just try with exponential function, right? So let's take e to the x. Let's say you know nothing about second order, how to solve the second order, and you simply try exponential function, right? And you do that, right? You plug it in. You factor out. Wow. It's doing something, I guess, right? Yeah, that's good. So this one is never goes to 0, right? This one never goes to 0. So this one goes to 0, right? All right. So we just verified that exponential function will work to solve this type of differential equation, right? Let's generalize one more time. One more step. That's e to the lambda x. Lambda is a number. Okay? We're just generalizing this, another the more general case, right? Doing the same thing. Lambda e to the lambda x. Oh, sorry, just 1 prime. So this is 2 prime lambda square e to the lambda x. And we plug it in and we factor out e to the lambda x. That will be lambda square plus a lambda plus b is 0. Okay? We just plug it in. And we have this famous, very important equation, a new equation. We are getting it. We didn't do nothing, but simply we plug the exponential function with the most general form, right? And then we get a new equation, right? But it's not a differential equation, but normal equation, algebraic equation, which is, we call it characteristic equation. Okay? It's a second order. It's a characteristic equation. Why? Because it shows the characteristics of this differential equation. This second order, this is not a differential equation. This is algebraic equation, but it shows everything about this differential equation. That's why it's called characteristics. It shows the characteristic of this differential equation. All right? If you really understand this characteristic equation, then that means that you really understand this equation. Okay? Homogeneous linear ODE with constant coefficient. So characteristic equation is really important. All right? All right, so we need to, since we know, we found a new equation, we need to solve it, right? We need to solve it. This has solutions too, right? The root, we call it root. And we gotta, get the roots of those equation, right? So from your preliminary methods, the root equation is this, right? Plus square root of a square minus 4 times b, right? And the other one is lambda 2 is 1/2 minus a minus square root of 4b. Okay? It's a solution of the previous characteristic equation, right? Plus minus square root of something. You familiar with this, right? The roots of that second order quadratic equation. And then, since we started with this assumption, not that assumption, but this assumption, okay? Y is e to the lambda x, and we have 2 lambdas, right? So our y1 is e to the lambda 1x, right? Which is e to the 1/2 minus a plus a square minus 4b x. And our y2 is e to the lambda 2x, which is e to the 1/2 minus a square minus 4b x. Okay? Right. But as you know, we have things to challenge and solve, right? Because of this square root, right? We gotta have 3 different types, 3 different cases, right? Okay, the first type. So the first type, if a square minus 4b, the inside of the square root, okay, is greater than 0, you see that? Then lambda 1 and lambda 2 are different, right? And they are real numbers. They are different, but they are real numbers, right? So we have 2 different roots, okay? So we have 2 distinct is different, okay? Distinct roots. And second case is if a square minus 4b is 0, right? If they are 0, then lambda 1 and lambda 2 are the same, right? And we have only 1 lambda. That's the problem, right? And those are still real numbers. So we have 1 double root. So just 1 root, meaning just 1 root. But it's doubled. It's the same, okay? And thirdly, if a square minus 4b is negative numbers, okay? If it's a negative, then it's a complex number, okay? So lambda 1 and lambda 2 are different, but they are complex numbers, not real numbers. So it's called complex conjugate root. Those are the three types by the analysis of the characteristic equation. Alright? Okay, so I'm going to talk about the three types, okay, how you derive solutions for each three cases. Right. So the first type, lambda 1 and lambda 2 are different. They are real numbers. Okay. Then your y1 and is e to the lambda 1x. It's quite simple, it's straightforward. Okay. There's nothing challenge for this case. You're just simply doing it. All right. So let's take an example. Example will give you, much better intuition on this. So, because it's too straightforward, y prime minus 2y is 0. Okay, let's say you have this differential equation, and this is definitely r is 0, right? And the coefficients are 1 and minus 2. So it's definitely the equation type that we want, right? All right. So y is e to the lambda x. That's what you need to do first, okay? And y prime lambda e to the lambda x, y double prime is lambda square e to the lambda x. Okay? And you substitute in, and you definitely, factor them out. Right? This is lambda minus 2 is 0, right? And so your characteristic equation is this. And the root of those are lambda 1 is 1/2 minus 1 plus root 9, which is 1. And lambda 2 is 1/2 minus 1 minus square root of 9, which is minus 2. Okay? So the calculation is quite straightforward. So you have two different. They are different. Lambda 1 is 1, lambda 2 is minus 2. They are different, and they are real numbers. Okay? So your answer will be C1 e to the x plus C2 times e to the minus 2x. You simply plug 1 and minus 2 in here, right, to get y1 and y2. So I'm going to move on to the next case, the second case. This is a little bit tricky because you need to use the reduction of order because you have only one solution. Okay? From the characteristic equation, you only get one lambda. So you have only y1, right? So to get y2, you need to use reduction of order. The second case, right? Alright, so second case, which is lambda 1 is lambda 2, and they're real numbers, but only one things, right? So, from this one becomes 0, right? So you have only minus a over 2. Okay, that's all. So lambda equal minus a over 2. You have only just one lambda, right, from the root equation, root formula. So your y1 equal e to the minus a over 2x. Okay? And y1 prime is minus a over 2 e to the minus ax over 2. We don't have to calculate, y1 double prime. Okay. But anyway, yeah. let me write it lambda 1. It's okay. So this means that we know one solution, right? That means we know just one solution. Okay? And then we have to use reduction of order. By assuming y2 is u times y1. Okay? And this is a function. U is not a number. This is a function. Alright. Then y2 prime is u1 y1 plus u y1 prime. Okay? We're doing the same thing. y2 double prime is u double prime y1 plus 2u prime y1 prime plus u y1 double prime. We just did for the reduction of order, right? And we plug it in to the equation, then u double prime y1 plus 2u prime y1 prime plus u y1 double prime plus a times y prime, right? You remember? So u prime y1 plus u y1 prime plus b times u y1. Okay? And we factor, with respect to u's, u1 plus u prime I'm doing the same thing, same stuff. Okay, plus u times y1 double prime plus a y1 prime plus b y1. And we know that this will goes to 0, okay, because it's a solution. And then, wow, we're getting into trouble. Right? This one we don't know. But luckily, for homogeneous linear constant coefficient type, this one is 0 also. Why? 2 times y1 prime is this, right? That is a times y1. If you add them up, then that's 0. Okay? That's because this is this case. Okay, the second case, in that case, that one goes to 0. Alright? Then, wow, we are lucky to have this relationship only. U double prime is 0, and simply we are just integrating up, right? By doing u prime is c integral constant, right? I'm gonna writing it to let you know, better understand. And u is cx plus c star, right? Now, y1, our y1, y2 is, u times y1, right? So we have u and we have y1. So ours is cx plus c star times minus a over 2. Oh, sorry. Times e to the minus ax over 2. Correct? Okay, then we, rearrange it a little bit. So c star e to the minus ax over 2 plus c tilde x times e to the minus ax over 2. Alright, so far so good, right? But then, the final form, y is c1 y1 plus c2 y2, right? So I'm gonna put this. You're gonna know why. And c1 is e to the minus ax over 2, correct? Plus c2 y2 is this, right? That's y2. That's your y2. C star times e to the c star times e to the minus ax over 2 plus c was wiggle, right? Times x times e to the minus ax over 2. Correct? If you rearrange it, c1 e to the minus ax over 2 plus c2 times c star times e to the minus ax over 2 plus c2 c tilde x e to the minus ax over 2. Right? But then this merges to c1 e to the minus ax over 2 plus c2 x e to the minus ax over 2. Okay? So all the integral constant will be submerged into c1 and c2. So you don't need to worry about the integral constant here. You didn't consider integral constant here. It could be just x, and at the end only this x left, okay? And all the integral constant, is included in c1 and c2. Okay? All right. So that's the second case. Okay, so I'm going to explain the third case. Third case, which is this. When the inside of the square root is negative number, okay? This is less than 0, then we're going to get complex number, definitely. Example 4, it's quite straightforward too. Y double prime, y prime plus 0.25, y is 0. Okay? If you get it, the next time you don't have to do this all the time. Okay? As long as you understand it, the straightforward method is lambda square, right? Plus lambda plus 0.25. You will be immediately get the characteristic equation right away. Okay? So this power, the number of power, becomes the power of lambda, right? And 1, reducing it, is 1. And there is no derivative, meaning 0 power. So lambda to the 0 is 1, right? Okay? Then the root of this is lambda is minus 0.5. Only one root. Okay? So in that case, you have y1 to be e to the minus 0.5x. Okay? So you have 1. And you already know that since this is just one reduction of order, it's x, right? U is x all the time. The simplest one. Okay? So y2 will be x times e to the minus 0.5x. So your y will be c1 e to the minus 0.5x plus c2x e to the minus 0.5x. So for the third case, the negative numbers. Okay? So the third case, lambda 1 and lambda 2 are different. So we have two distinct values, but it's complex numbers. Alright, so lambda is, from that equation, that lambda 1 is plus I omega. Okay, I'm going to explain why we are using omega. Lambda 2 is minus 1/2 a minus I omega. Okay, that's plus minus square root of, and that square root of is negative value. So our omega is a square. Okay, the omega is for simplicity. Okay, it becomes complicated, so we want to make it simple. There's a reason why it should be omega. We can use K, or we can use L, we can use other alphabet, right? But omega, it has some physical meaning. Why we are choosing omega? It has physical meaning. to be choose, omega. I'm gonna explain later. So, but anyway, it's just a symbol that represent the complicated terms, okay, with simplicity. So, our y1 is definitely minus 1/2 a plus I omega times x, right? That's our, stuff. And that is e to the minus 1/2 a times e to the I omega x. I'm sorry, ax. Right? And y2 is e to the minus 1/2 a minus I omega x, which is e to the minus 1/2 ax times e to the minus I omega x. So that's our y1 and y2, and those are bases. Those are a bases. Okay? Then I need jump. I told you jump, okay? Jump on logic. I have to say, I don't want, but I have to. There's no choice, I guess. So our basis, y1 is e to the minus ax times cosine omega x. And our y2 is e to the minus 1/2 ax times sine omega x. Wow. Look at that. From this y1 and y2, our final basis is to be said there is no I, right? It's a real number and just sine and cosine, the function that we are familiar with, right? For me to, explain it accurately, that's long story. I mean, that's a long way to go. So I have to, let you know there's a jump there. But as long as you accept this jump, I'm going to explain a little bit, but as long as you accept this jump, your life is, easier by assuming this. C1, y1 plus C2, y2, and C1, is e to the minus ax over 2 c1 cosine omega x plus c2 sine omega x. Okay, so final answer is quite normal as it is. Okay, no complex numbers, nothing special function there, right? Quite understandable. So you have to kind of accept it. You have to kind of a little bit memorize it. Okay? But I'm going to explain this jump a little bit.